In this class, let us learn Gauss's law. Consider a spherical surface around a point charge. The charge is at the center of the sphere of radius r. Divide the surface into small area elements. The flux through a small area element delta S, delta phi is equal to E dot delta S. The area vector delta S is parallel to the electric field. So it is equal to E delta S. The total flux through the spherical surface is obtained by adding up the flux through all the area elements. So phi is equal to summation delta phi or summation E delta S. Since the electric field is constant or the magnitude of the electric field is same at all points on the surface of the sphere, it is equal to E into summation delta S. Summation delta S is the surface area of the sphere S. So phi is equal to ES. Electric field due to a point charge is 1 by 4 pi epsilon 0 into Q by R square, and the surface area S is 4 pi R square. So phi is equal to Q by epsilon 0. This is known as Gauss's law. Total electric flux through a closed surface is 1 by epsilon 0 times the charge enclosed by the surface. Now let us apply Gauss's law in a region of uniform electric field. Consider a cylindrical surface. The total flux through the cylindrical surface phi is equal to phi 1 plus phi 2 plus phi 3. A cylinder has three surfaces, two end faces and the curved surface. So it is E dot delta S1, which is one end face, plus E dot delta S2, the other end face, plus E dot delta S3, that is a flux through the curved surface. For the left end face, area vector is opposite to the electric field. So E dot delta S1 is minus E S1. S1 is the area of the end face. And for the second end face, area vector is parallel to the electric field. So E dot delta S2 is plus E S2. S2 is the area of the other end face, plus 0, because for the curved surface, area vector is normal to the electric field, so the dot product is 0. But S1 is equal to S2, so the total flux through the cylindrical surface is 0. So we can conclude the total flux through a closed surface is 0 if no charge is enclosed by the surface. The surface considered is known as Gaussian surface. Let us consider another case in which a cylindrical surface encloses a dipole, a system of equal and opposite charges separated by a small distance. The total charge enclosed by the Gaussian surface is 0. So the flux through the surface is 0. But electric field is not 0 around the dipole. So let us conclude. Gauss's law is true for any closed surface irrespective of the shape and size of the surface. Phi is equal to q by epsilon 0, where q is the charge enclosed by the surface. For this surface, the enclosed charges are q1 and q2. So the enclosed charge is q1 plus q2. And flux phi is equal to summation E dot delta S. But the electric field at any point depends on q1, q2 and q3. But flux depends only on q1 and q2. The Gaussian surface cannot pass through any discrete charge, but it can pass through a continuous charge distribution. In a medium of permittivity epsilon, phi is equal to q by epsilon, where epsilon is k times epsilon 0. K is the dielectric constant or relative permittivity epsilon by epsilon 0. Now let us see continuous charge distribution. If a charge is uniformly distributed on a metal wire or on a metal surface or in a metal body, the charge distribution is known as continuous charge distribution. For a metal wire, the linear charge density lambda is defined as charge per unit length. So the charge enclosed by the cylindrical surface is lambda into L. For a metal surface, the surface charge density sigma is defined as charge per unit area. So the charge enclosed by the given surface of area A is sigma into A. And if the charge is distributed uniformly throughout a volume, then volume charge density rho is defined as charge per unit volume. So the charge enclosed within a volume is rho into volume. Unit of lambda coulomb per meter, unit of sigma coulomb per meter square, and unit of rho coulomb per meter cube. Thank you.